Hello, good evening. So welcome to the ninth week of NPTEL regression tutorial classes. So today I'm going to talk about from where we left in the last class, where we were talking about weighted least square method. Weighted least square method. Okay, so suppose if you have a linear model, simple linear regression model. Suppose you have a simple linear regression model that is called SLR. Y is equal to beta naught plus beta 1 xi plus epsilon I, where y is your response variable, xi is your regressor variable, beta 1, beta naught, and beta 1 are your regression coefficients, and epsilon I is your residual term. So again, I will repeat. So we are trying to fit a model given we have been given, suppose in the data you are provided with xi's and yi's, n values of these two parameters, where yi's are your response variable and xi is your independent or regressor variable. So the response variable is dependent on this regressor variable through this equation. So in order to fit this data, in order to get a linear fit to this data, what you do is that you set up a model which is written like this. So this model can be linearly fitted by finding this regression coefficients, this regression coefficients, and but there are certain assumptions. There are certain assumptions which are important with regard to this for linear regression model in common. It can be simple or multiple linear regression model. And one of the out of many assumptions, one assumption which is very important is that the residual epsilon i's, they are identically independently distributed, normally distributed with mean zero and variance sigma square. So if you pick up these residual term from the population, then that population will have a mean zero and variance sigma square, and it will be normally distributed. And all these EIs will be independent to each other. But suppose given some data, you fit it. You fit it using ordinary least square method, ordinary least square estimate, ordinary least square estimate method. Okay, so and you get a fit, and you plot after getting a fit, after getting an equation, after getting a fit, I mean after finding beta naught and beta 1 values, After finding this beta naught values, you can put it up in this equation. So you will get a linear equation of a linear model. And then what you do is that you plot the residual plot, between the residual EIs and the estimate and the model estimated response variables yi cap. Okay. So you know how to find these EIs. EIs is nothing but the difference between the original response variable, ith response variable. So the ith residual is equal to the difference between the ith response variable, which is given in the data, minus the ith response variable predicted by the model, represented by this cap. So after you find this, and you already have this value, so you just plot on xy axis. We will change some color. So take on xy axis. Sorry, I'm sorry. Now it will find. Okay, now you plot an x on xy axis. These on the x-axis you will take the model estimated yi's or yi cap. On the y-axis you will have these residuals ei. So you just plot these residuals, and suppose this is a constant e line. So I will take. You can have two cases. Okay, so suppose this is E is equal to 0 line, that is, there is no residual, so the model is perfect, it is able to predict your response level accurately. So in that case, if you just plot the scatter plot, this is a scatter plot or residual plot. I taught it in 2 class before. So you will plot. Now, if your scatter plot looks like this, then you would say, so if your scatter plot is look like this, that is your residuals are uniformly distributed about this E is equal to 0 line. That means the variance of your response variable is more or less constant. Because if we go in increasing the value of y, the residuals are also not changing much, so they are uniformly distributed about this E is equal to 0 line, and it implies your model is doing a good job. But suppose when you plot this residual plot, this is a residual plot. When you plot your residual plot for another model such that this is E is equal to 0 line, such that your scatter looks like this. So it appears in this case. So let me mark this as one case, and now in this case the variance of y increases as yi increases, as you can see in this case. First thing, because what we call this as outward funnel. We call this as something like outward funnel residual plot. So in this case, what you see is that your variance goes on increasing as you increase the value of y. Okay, so it implies that the assumption of constant variance in a linear regression model is violated. Your variance, which has this normally distributed in your model, the variable random variable associated with the model is normally distributed with mean zero and variance sigma square. But you see that no, variance is not constant. With increasing value of y, variance also goes on increasing. Or opposite can also happen. You can have another case where you can have something like invert funnel, where the variance goes on decreasing if you go on increasing y. So this is in that case also your variance is not constant. So the point is that the assumption of constant variance is violated in this case. So we need to find an alternative way to fit these kind of model. Okay, because the variance is the constant variance assumption is violated. So in order to do this, wait, let me take this down. It will come later. Yeah. Okay. So to deal with the violation of constant variance assumption, we come with another technique which is called weighted least square method. A weighted least square function. Okay, or method, I would say. So in order to apply this weighted least square method, we need to find a function called weighted least square function, and that weighted least square function is given by which is we know that in the simple linear regression model, your we do this fitting by minimizing a function called the residue s function, which is nothing but summation I y I minus yi cap. So this is your function. So we minimize this function, or this can be written further as epsilon I, sorry, summation I yi, and your model is what? Your model is beta naught plus. So you just subtract it minus beta naught minus beta 1 xi. So this is your s. So you take the derivatives, you minimize it. So you take the derivative and then you estimate betas. You find beta 1 and 0, beta naught and beta. Normal equation, two equations will get you will find two parameters. Now suppose yes, this is for a simple linear square or ordinary. This is a for simple for simple linear regression model. You do a ordinary least square estimate. No, for a weighted simple linear regression model, you can say you do a weighted least square estimate, where what you do is that the function remains same almost, just a slight modification. Now this is nothing but this is your residual skull. Okay, so you just add a weight term wi for each observation. So for each ith observation, you have a corresponding weighting term. So you weight each of your y, this estimate this quantity with another weighting term, which we need to estimate. So your function gets modified, and now you just minimize. You minimize this. You take the derivative and you estimate your regression coefficients. Okay. Now, in order to do this weighted least square estimate, since we have added this term, it is important to find this term. Now, one thing which we discussed in the last class is weight terms is inversely proportional to the sample variance sigma I square. So in order to estimate a response variable, so this is the variance of the population from which you are getting your response variable yi. So this weight is one of the properties that this weighing term is inversely proportional to the variance of yi. Yeah. Where we already yeah. So I already told. Now we minimize it and you find beta. Now, so since I already told that how to do that, we have to first, if we given a data, first we'll do what we'll do is that we did the all linear fit, and then we'll do this. So let us take an example. We'll just take an example over here, and then we would see that how we can apply this theoretical part in solving questions. Okay, so this is the I have taken from the lecture. This example. So this is courtesy NPTEL lecture 9 by Professor Somenati. So, given this, so we have some data. So, this data is provided to you. This data is for some restaurant food sales data. So, there are total 1 to 15, 30 observations, which we have. Total number of 30 observations. 15th here. Yeah, 15 here, and then rest of total 30 observations. And your response variable yi is your income, that is income which you are having in the restaurant income. And on the regressor variable which we have here is xi is the advertising expense. So suppose you want to fit a model between these two data points, xi's and yi's, linear model. So as I told, first you just go with the ordinary linear square estimate. In that method you just take these datas and you just do a linear fit. So uh, when we just do the first step is, maybe I will little bit small. Yeah. So steps for weighted least square estimate. First of all, you would do ordinary least square estimate. So you'll just take this data and you'll just find beta naught and beta 1 using this ordinary least square estimate method. And then you will fit the data and you'll have something like this, which for this particular problem, y cap is 49. This has been calculated already, 443 plus 8.0484x. This is your fitted model using ordinary least square estimate. Second step, calculate the residual. So for calculating residual, you for each observation, so you will have yi minus yi cap. Third step, plot the residual plot. I already told you last 15 minutes this thing only. Plot the residual plot between ei versus yi cap. Okay, so this model has been fitted, and for this model, if you just calculate these EIs and then plot the residual plots, so the residual plot will, for this particular, will look like something this. So yeah, always draw this least equal to 0 line for the reference. Now, when you plot the for this given data of restaurant sale, if we just calculate this EIs, so it comes something like this. So as you can see, that for this particular data, your residuals. Can you just excuse me for 1 minute? Just 1 minute. I will just. Yeah, sorry for the interruption. So yeah, so what I was telling is that for this restaurant sale data, if you just plot this restaurant plot, then you'll see that your variance goes on increasing as by increase. So that means that constant variance assumption is violated over here. So variance is violated. So that just mean that constant variance assumption is violated, and hence it is a particular example of that outward funnel. So it is just a perfect example of outward funnel residual plot. So yeah, so that means it implies that the ordinary least square estimate is inappropriate to fit these data. Inappropriate to provide a fit to this linear fit to this data. Therefore, we go for the weighted least square estimate. Okay, so now what we'll do is that we'll go for the weighted least square estimate. Okay, so for the weighted least square estimate, for the weighted least square estimate, we have to minimize this function, which has this weight term wi. Okay, so and we know that wi is inversely proportional to the population sample variance. So to do the weighted least square estimate fit, we need to find the weights wi, and wi can be find can be found if we know the variance, if we know the sigma I square, because we have this relation. Okay, so what we'll do is that we will consider not estimate sigma is. What we'll do is that we will consider all the x values which are very near to each other, like 3000, Similarly, these two values are very near to each other. Similarly, these five values are near to, and so on and so forth. So we'll do a clustering where we will cluster the x values only, not y. The only x values will cluster into different segments or clusters, with each cluster having a very near equal x values, and then we'll calculate a mean of this. Okay. Then we will just calculate the mean. So for example, the mean of the first three values is 3078. The mean of these two values is 52. Similarly, we'll calculate the mean for all the clusters. So we'll estimate x bar. And similarly, what we'll do is that After that, we will compute sample variance sy square for the corresponding y values. For example, we'll take these three values and calculate the sample variance. So what is sample variance? So I will write how to estimate sigma. This is a suppose this is a question how to estimate sigma square. So what we'll do is that first we consider all x near equal values of si and cluster them. Okay, so we'll take all near values of xi and then we'll cluster them and then find x prime. Secondly, what we'll do is that uh, then calculate the sample variance for the response variable yi for each cluster. Now this sample sample variance is given by this sy square. So sy square is nothing but 1 upon n minus 1 summation is equal to 1 to n yi minus y bar whole square. So for example, you'll calculate for these three values, you will calculate y bar and then you take I minus y bar, square it, and then we'll divide by n minus 1, that is 2. So you'll get a sample variance which is corresponding sy square. Similarly, you'll calculate sample variance for each of the cluster. So what you will have is that you have x bar and you have sy square, that's sample variance. You do a ordinary least square estimate of fit for these data now, x bar and sy square. So you'll get an equation which is something like minus 737,621. This is for the restaurant sale data. 7819.77 x bar. Now, interestingly, this fit is linear. If you just see, as you go on increasing the value of x, your sy square will also increase. So if you just do a scatter between xi and yi's, x bar and the sample variance sy square, if you just do a scatter plot between x bar and the sample variance, you will get something like a kind of linear fit. Okay, so for a given cluster, the response is coming from a population that has variance as y square. Okay. Now, after we have found this equation, what we'll do is that, suppose this is equation A. So after that, what we'll do is that you will estimate using this sample variance, you will estimate sigma I square by just putting, okay, fourth, estimate the population variance by substituting or maybe putting, not substituting, each xi value into equation A. when you'll do this, when you'll put this for each xi, will put this value in place of x bar. In place of x bar. So for each x bar, you will put the xi values, and then you will get sy square. So you will estimate for n number of xi's, you will get, we will get n number of sigma I square, and that is what. And using those n number of sigma I square, we can estimate wi. Wi is equal to 1 upon sigma I square. So you will just put the xi value into this equation. So there are n number of xi values, so you will get n number of this sy square, which is nothing but sigma I square, and then you will get n number of weights. By just weight is just inversely proportional to the sigma I square. That is a property which I've already told. So after this, what you do is that you will just put this, and you will get, as you can see, these weights. So given this column, so all these weights. So all these weights. So these are calculated by just taking the inverse of the uh, variance. So once you have found that inverse of the variance, now minimize S, which is equal to Wi yi minus beta naught minus beta 1. So just minimize, what are yi, these all values, not wi also, so you can estimate, using this estimate, you can calculate this beta naught and beta I, because xi is known, y is known, wi is known. So you can just, using that older method, you just find this, you'll just differentiate this, and then you'll get your betas and beta 1, okay, and using that beta 1, your linear fit comes out to be like this: 50975.56 plus 7.9222x. So this is your final estimate. This is your, this is a weighted linear model, regression model, using weighted least square estimate. Now, sixth step is what? Now, for this particular model, you compute the residual, and plot the residual plot. For this case, the residual plot will be between wi to the power 1 by 2 epsilon I versus yi cap. So when you do this residual plot, so what you'll find is that this is, on the y-axis you have the residuals, on the x-axis you have the model predicted yi. So now you see that clear improvement is seen as your variance does not fluctuate that much, does not fluctuate inhomogeneously about the line is equal to 0. We can see now the variance is more or less homogeneously distributed about this e is equal to 0 line. That means your model is improved. Because earlier, when you fitted the model using ordinary least square estimate, you got something like this, where you see that variance goes on increasing. But here, the variance is more or less constant as we go on increasing by a value. So, the weighted least square method gives a better linear fit. So, the assumption which the constant variance assumption is now held, it is not violated. So, so this is basically why we use a weighted least square estimate method. Now, what I will do is that I will try to solve few questions which was there. So maybe I will solve some assignment questions also. So just give me 2 minutes. Okay, so now, okay, so now we'll move ahead. Just give me one more minute. I think the page limit has ended, so let me have I have to increase it. Okay, so some questions. So suppose I think we'll just go through the lecture, the assignment 9. Then there was one question which they've asked is they ask you to fit a model with I guess no uh, intercept. That means your beta naught term is 0. So your model is just yi is equal to beta xi plus your epsilon I using weighted least square estimate where your weights wi is equal to the variance of your response variable, which is nothing but a function of the regressive variable itself, kxi square. So your weight term is equal to kxi square, kxi square, where xi is a regressive variable, and this is your actually sigma I square. Okay, so you already know sigma I square, and once we know sigma I square, we can easily have the weighted least square estimate. So we'll take from the zeroth principle to solve this, and what we'll do is that so we have to fit this model. yi is equal to beta xi plus epsilon I. Okay, so we know first we need to minimize this function, which is and yi minus your model, and your model is what? Model has just beta. It has no beta xi. So this is you have to minimize this function. Now wi is has been given to you. It is kxi square. Wi is equal to sigma I square is equal to kxi square. Okay, so this is given to you. So we'll just substitute this. So what you'll get is, so it is okay. Sorry, wi is 1 upon my mistake. It is sorry. One mistake. Yeah, variance of y, which is equal to sigma I square. This is equal to 1 upon kx square. Okay. So your weight is equal to 1 upon what I'm doing. I think weight is equal to I was right only. Just sometime you just get confused by some notations. There's no point of getting confused, but yeah, it can happen. So it is kxi square. So now your weight is equal to, as you know, 1 upon sigma I square. So it will be equal to 1 upon kxi square. So you just substitute this in this equation. So you get 1 upon kxi square yi minus beta xi square. Now you just differentiate it. You have to minimize this function. So you just differentiate it with respect to beta. So when you do that, you will get del by del beta of this quantity epsilon I 1 upon kxi square yi minus beta xi whole square. Okay, and now when you'll just differentiate it, so k will come out, it is a constant term, and summation will be there as it is. So you will be 2 times yi minus beta xi times of minus of xi. Now this should be equal to 0. So what you left it is okay, and you also have one in denominator you have this xi square term. Okay, so that will be also there. So this is xi will cancel, so you'll have finally so I two will also go, so you'll only have yi upon xi minus beta is equal to 0. Now you can distribute this summation. So one will get yi divided by xi is equal to summation of I beta. Now this I runs from 1 to n since you have n observations. So this will become, I will write, this will become n times beta. Because beta is constant, so it just beta will come out. Beta will come out, so it'll just summation I is equal to 1 to n 1. So it just add 1 n times, so it will become n. So you will add 1 4 times, it will become 4. You will add 1 6 times, it will become 6. So you will add 1 n times, it will become n. So finally you will get your beta estimate is 1 upon n summation of I yi upon xi. So this is your final answer for this question. This is your answer. So your beta is I estimate of beta is 1 by n summation I yi upon xi. Now this is question 1. Now question 2 can come for the given model in 1, find the expectation value of your beta. Find the expectation value of your beta. Your beta estimate. So expectation value of beta cap. Okay, so this is also can be solved. We know that beta we just found is 1 by n summation I yi upon xi. So the expectation will take e of on both sides. So expectation value of beta cap is expectation value 1 upon n summation I yi upon xi. Okay. So this is your expectation value, and uh, this is say equation 1. Okay. You can just even leave it. Don't no need to name this equation 1. And then you can further simplify it. Since n is constant, it will come out. So you can write it 1 by n expectation value of summation I yi by xi. Now you can do a further substitution, and you can write this as expectation value of Ci yi, where Ci is what? Ci is summation I 1 upon xi. Okay. Now you can take this inside, and so it will become, since your yi's are independent, and so you can just take it inside, and it will become this. And we know that for a given model, we have a simple model with no beta naught. We have only beta. This is a model. So the expectation value of pi I is what? Expectation value of beta xi plus expectation value of expectation just give you the mean of that particular. Now, always remember, I told in the second class also, this in this linear regression model, your yi and epsilon I are random variable, whereas your xi is control variable, and the expectation value of the control variable is always the same thing, that is expectation value of the control variable will be the same, beta xi, and the variance of this control variable will be 0. And from the assumptions, we know that the residual have mean 0 and variance sigma square. So since the mean is 0, so expectation value of this residual term will be 0. So your expectation value of y will be just beta xi. You'll just put this over here and you will get ci times beta xi. Now you just put back ci value. Ci is what? Ci is ci is this. So you'll just put ci. Ci is summation I 1 upon xi and beta xi. This will cancel out. I is running from I is equal to 1 to n. So it will become 1 upon times n times beta. So n cancel. So beta. So expectation value of the estimator beta is beta itself. So this means, this implies that beta cap is an unbiased estimator of beta. And this is the answer. So you have to just click select this option. So this was the answer of the second question. Now similarly, they have one more question. Question 3. For the given model in question 1, estimate the variance of beta cap. So on similar grounds, we can also solve this question also. So the solution is, we need to find the variance of beta cap. So variance of beta cap can be simply written as variance of 1 by n yi upon xi. Now what we'll do is that we'll take out this property. We know this property, the variance of constant a times x is a square variance of x, where x is your random variable. Similarly, we'll apply this. So 1 by n is constant. It will come out. It will come 1 by n square. And variance of summation of yi upon xi. Similarly, as we did in second question, we'll just make a substitution, and we will write this as ci times yi, where we know that ci is already defined in the last question. 1 upon xi. Okay. Now you'll use this property only, so you'll just it will become cia square times variance of y. Okay, and variance of y in the question we already know is given as k times xi square. Variance of y they've already given in the question is kxi square. So you just put this. So I have to write this clearly. People can get confused. N square, n square. Okay. Now I will just put back the value of ci, which is k is constant, so k can come out. So k upon n square. Ci I will just put it back. So ci is it, then ci square is nothing but epsilon I 1 upon square. Okay. So I will just put I is equal to 1 to n. Ci square is 1 upon xi square and xi square. Now this will get cancelled out. So you'll just be left with k upon n square summation I is equal to 1 to n 1. So it will be k by n square times n. N cancel. So k by n. So the variance of your estimated beta cap is nothing but k by n. So this is the answer for this question. Yeah, so this is the how I've solved 3 questions from the assignments. So they have to ask a different question they have asked you and then they ask you some more questions also, which I will just take. So let me see what are the questions which they asked. Okay, so I'll just go down. Yeah. So another question which was asked is given a model where the variance of the response variable y is sigma y square and it is proportional to the expectation value of y, find the variance stabilizing transformation. So in order to solve this, I will just get back to that table which we just derived a table for a general case where suppose you have a model which does not have a constant variance, and suppose you want to transform it into another model which has a constant variance using this variance transformation. So various stabilization transformation function actually they've asked you. So I will just take back to you the what is all this. You just have to maybe I have written somewhere. must have written it. Yeah. Yeah. So basically, in this question, they have given you that the variance is directly proportional to the expectation value of y. So it is this case. So expectation value of y means mean. So what is the variance stabilizing factor? So variance stabilizing factor can be found by this formula Fy, which is equal to y to the power 1 minus q by 2 and log y. So in case where q is your okay, where your suppose your variance is in this form, it is a function of mean, and q is the power of the mean. So in this case, since your expectation value is just equal to mean, so your power of q is equal to 1. So if you just put q is equal to 1 in this equation, so it will become 1 minus 1 by 2 root y. So your variance stabilizing factor of this for this question will be, so I will just write it, y to the power 1 minus q by 2. So variance stabilizing factor is given by Fy, and Fy is equal to go back and see, it is given by y to the power 1 minus q by 2. Y to the power 1 minus q by 2 for q is not equal to 2, and log of y. So this you can be remember for solving questions. So in our case, since where uh, if variance of y is proportional to some k times mu to the power q. So here in given question, your variance is directly proportional to mu. So your q is 1. So just put q is equal to 1. So your variance stabilizing factor will be y minus 1 by 2. So it will become root of 5. So your variance stabilizing factor for this particular transformation is f of root of 5. So this is your answer. Similarly, in the next question, they ask you question 5. Suppose you have n observations of variables, and where xi's are regressive variable and y is a response variable, and y's are exponential variable. So we consider a model fitting. Okay, so suppose there is a model where you have yi's and xi's, and xi1, xi2 up to xik minus 1. So k minus 1 regressive variables. So what is the reasonable choice of, so here your y's i's are exponential variables. So for exponential variables, from statistics you will know, for exponential variables, your variance of the response variable, which is equal to sigma square, is directly proportional to the square of the mean. So here q is equal to 2. So for q is equal to 2, your variance stabilizing factor is just log of y. So your answer would be log of y, natural log of y. Okay, so this will be your answer. And similarly, question they ask another question, question 6. Another same thing. It is for a Poisson variables y. If your yi's are not normally distributed, but they are Poisson distributed, find your Bayesian stabilizing factor Fi. So for Poisson distribution also, your for Poisson distribution, the expectation value of y is equal to mean only. So here also q is equal to 1. So the variance stabilizing factor f of y is nothing but y to the power 1 minus 1 by 2, which is equal to root of y. Okay, so I think this is what it needed to solve. I hope. Let me just cross check it. Let me just cross check it. Yeah, it's fine. It's fine. Okay, so in this way, I have solved total 6 questions, which was asked in the last assignment. How to solve it in case you have some problem. So this is how to solve it. It can help in your final exams. Okay, so now since we have completed this ninth module, so next module, that is in 10th module, we are going to discuss a new topic called dummy variables. Called the dummy variables. Okay, so today we covered almost this weighted least square estimate method is covered today. So okay, if in that case we'll meet tomorrow to discuss the 10th week lectures. So thank you for coming and watching.